The first law of thermodynamics, there is no free lunch. Now, at my children's elementary school, every child gets free lunch. Is it actually free? No. Somebody's paying for that, right? It's just not the children. So there's no free lunch. There's nothing that's really free. Everything costs something. First law of thermodynamics. What's thermodynamics? Thermo is referring to energy, and the dynamic, things changing, right? So it's the study of energy and the interconversions between energy. So other than saying there is no free lunch, the first law of thermodynamics really is just the law of conservation of energy. Another way to say it is the total amount of energy in the universe is constant. You can't make energy. You can only get it from some other source and convert it into something that's useful to you. Have you heard of I can't even say it. Have you heard of perpetual motion machines? Anybody? Yeah. So people, they're tinkering and they're like inventors and, oh, cool, I made this thing and it just keeps going forever. And we could figure out how to harness this and we'd have free energy. All of those perpetual motion machines were found to have some unrevealed source of energy behind them. There's no such thing as something that will just keep moving indefinitely without any incoming energy. With energy, you cannot get something for nothing. It's always going to cost you. So this is a very important concept. The conservation of energy requires that the sum of the energy changes must be zero. So the change in energy for the universe is zero, no matter what we do. That means that the change in energy for the system plus the change in energy for the surroundings has to be zero. When we use this triangle, that's the Greek letter delta, it means change in, and it's always the final amount minus the initial amount. And we'll see that in several different situations. Delta means final minus initial. So what the system lost, the surroundings gained. It's a little bit like money. So yesterday I gave my son a ride to school and he's like, Mom, can I have some money for lunch? All I had was $2. So I gave him $2. I lost $2. He gained $2. The $2 didn't get bigger or smaller. They didn't cease to exist or come out of nowhere. They just got transferred from me to him. So it was minus $2 for me. It was plus $2 for him. Energy transfer is the same way. If I lose it, something else has to gain it. Now, it doesn't always have to be the same thing. I could give $1 to Tommy and $1 to Michael. But you get the idea, right? So internal energy is what we call capital E. So the internal energy of a system is the sum of the kinetic and potential energies of all the particles that compose that system. So it includes any potential energy due to being elevated, any potential chemical energy, any thermal energy, any kinetic energy it has. All of those added together. That's something that we can't really measure. You just can't. And it's changing all the time, so that makes it even worse. What we do look at, though, is changes in internal energy. So the change in the internal energy of a system depends only on the amount of energy in the system at the beginning and at the end. This is what's known as a state function. It's a mathematical function where the result only depends on where you started and where you ended up. It doesn't matter how you got there. So if I hand the $2 to Emily and she gives the $2 to Tommy, the net change is the same. I lost 2, he gained 2. Emily gained and lost 2, but the overall result is the same. It doesn't matter what happened to the $2 in between, it just matters before and after. So we say the change in energy, the change in the internal energy, is equal to the final energy minus the initial energy. We can talk about the change in internal energy occurring during a chemical reaction. It's the energy of the products minus the energy of the reactants. Always the final minus the initial. So to explain state functions a little better, we think about climbing a mountain. So we're starting here at the base where the elevation is 0, and we're going to go to the top of this mountain where the elevation is 10,000 feet. So there are 2 paths up the mountain. There's path A, where you don't have to go very steeply, but it's long. You're going to wind around, and this is 12 miles you're going to hike. Or you can hike straight up the side, and that's only 5 miles. Now you might care which path you take, but what's the change in elevation once you get to the top? It's the same. It's 10,000 feet. It doesn't matter which way you got up there. Personally, I'd prefer to get in a helicopter over here, go straight up, fly over here, and come back down, right? Change in elevation is the same. It doesn't matter how you got there. That's what a state function means. We use energy diagrams to help us visualize these changes in energy. So what we'll do is we'll have a y-coordinate here where internal energy is increasing as we go up. Usually we have increasing going up. For this chemical reaction, we have carbon dioxide being decomposed into carbon and oxygen. The reactant, carbon dioxide, has a lower internal energy than the products do. Not going into why that is, just say they found it out and that's what it is. So when this reaction occurs, we go from a low energy to a higher energy. Well, delta E is the change in energy. It's the energy of the reactants minus the energy of the products minus the energy of the reactants. So it's this higher energy minus this lower energy. Delta E is positive. It increased in energy. So again, I think of energy as being like money. If someone gives me a $20 bill, my energy, my money has increased. Do I view that as positive or negative? I think that's a very positive thing. When I have to shell out $10 here and $85 there for baseball cleats and this and that and the other thing, my money is leaving. Is that positive or negative? It's negative. I don't like that. I'd rather just keep my money. So energy increasing, delta E is positive. So the energy of the system increased. Where did the energy come from? The surroundings. We're kind of simplifying the universe here. We're saying, okay, this is my system. The surroundings are everything else. So you only have 2 things. You have the system and you've got everything else. So if this is increasing in energy, everything else must have lost the same amount of energy. If we take this reaction and run it the other way, and we combine carbon and oxygen to form carbon dioxide, now the reactants had a higher internal energy than the product does. And so product minus reactants, small number minus large number, is negative. Here the system is losing energy. That energy has to go somewhere. It goes into the surroundings. Any questions? Energy flows out of the system. All of it goes into the surroundings. When the system loses energy, delta E for the system is negative. When the energy flows into the surroundings, delta E surroundings is positive. So the magnitude of the change in energy is the same. The negative sign just tells direction. It's opposite in direction. When I gave Tommy $2, it was only $2, gave him $2. Well, the change for me was 2, the change for him was 2, but for one of us it was negative, and for one was positive. It's like transferring money between your checking and savings accounts, right? If you take it from your savings account and put it into your checking account, the change is the same, but it's negative for one and it's positive for the other. Any questions? Well, how is energy exchanged? It's exchanged through heat and through work. Heat is given the symbol Q. Don't know why. It is. Deal with it. Work is given the symbol W. That makes a little more sense. Heat and work are not state functions. It does depend on the process. But the change in energy is equal to the heat plus the work. Now, these can be positive or negative as well. If the heat is positive, that means that the system is gaining thermal energy. If it's negative, the system is losing thermal energy. So I lose energy, I lose money, that's negative. And we're always putting ourselves in the position of the system. What's the system getting? What's the system losing? For work. So if W is positive, that means that work is done on the system. So I think of that as maybe going to a spa and getting a massage, right? Someone's doing work on me. Is this positive? Yes, this is positive and pleasant. Negative is me doing work on something else. Me going home and washing the dishes. That's negative, right? It has to be done, but I don't like it. I'd rather not. So the change in internal energy, again, is positive if energy is coming into the system, negative if energy is going out of the system. The way that energy comes in and out is through heat and work. Any questions? You should remember this equation. It's not too tough. Delta E equals Q plus W. Let's go back to the pool table. So here we have a smooth pool table. This is a pool table in good condition. We take a white billiard ball here, and we're going to hit it and cause it to move. Initially, it has a kinetic energy of 5 joules. And so that's, depending on the mass, whatever velocity is required. So it's moving. What happens to pool balls as they move across the table? Do they go the same speed all the time? No, they slow down because there's friction, right? So as it's rolling, it's losing some of its energy due to heat. Okay, so rub your hands together. What do you feel? Warmth, right? When things have friction, there's heat. The kinetic energy of moving your hands together with the friction is causing thermal energy. So you don't notice that this is getting hot as it rolls across, but that is energy being lost as heat. So it loses 0.5 joules. By the time it gets over here, then it's not moving as fast as it was before. Here we have a collision that we're going to pretend is completely elastic. It's pretty close. So there's no loss in energy. That 4.5 joules of kinetic energy that it had left when it gets here gets transferred to the purple ball, which then rolls off. That transfer here is work. So we have the work that the ball did, negative 4.5. It did work on the purple ball. The heat was negative 0.5. It lost half a joule as it rolled across the table. The overall change in energy is negative 5 joules. Here its kinetic energy is 0. It's not moving. Okay, any questions? Did that make any sense? What if we have a rough table? This pool table's been abused, right? It's really rough. If the table's rough and you roll the ball, it's going to slow down a lot faster. There's more friction. So here it started with 5 joules, but it lost 3 joules of energy as it rolled across. It's going much slower now. It only had 2 joules left when it hit the ball. So it transfers those 2 joules from the white to the purple as work. But again, the change in energy is the same. How it happened is different, though. Energy is a state function. Heat and work are not state functions. Yeah, I kind of said all of that. Let's just jump down to here. Q plus W is the same for both tables, even though the individual values of Q and W are different. But Q plus W is the change in internal energy, which is a state function, does not depend on process. And so we get back to this. The energy that was lost by the first ball, we're defining the white ball as the system. The table and the purple ball are both part of the surroundings. So the energy lost by the system is equal but opposite in sign to the energy gained by the surroundings. Any questions? So heat is a transfer of thermal energy. This happens when the system and the surroundings have a difference in temperature. Okay, so whoever's got the hand warmers. So there's a difference in temperature between your hand and the hand warmer, and so the thermal energy is flowing from the warmer one to the colder one. And it will continue to do that until the two things become the same temperature. When they reach the same temperature, then there's no more heat flowing. And then we've reached thermal equilibrium. And so then the temperature is just going to sit there. Okay, so let's look at an example here. Like I said, we're just flirting with physics here, and so these are going to be relatively simple problems, but they're important to understand the concept behind it, because then we're going to get into some chemistry involving this. So here we've got a cylinder and a piston assembly. We're defining that as the system. It's being warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what's the value of delta E? Well, what is delta E in terms of Q and W? It equals Q plus W, right? So we've got two numbers here. We have 559 joules, and we've got 488 joules. We're told that the 559 is the heat, so we'll call that Q, and the work is 488. We have to determine the sign on these. Usually the problem is not going to say, well, Q equals negative this or W equals positive that. It's going to give you words that indicate direction, just like with money. So if I gave Tommy $2, we understand the direction that the money went, right? So the words here tell us the direction that the energy is going. The system absorbs this much heat. Is that positive or negative for the system? It's positive. Got money coming in. I like that. 480, it does 488 joules of work. It did work. That's negative. Okay, so that's how you decide the signs on these things. And then E, delta E, just equals the sum of those. So I'm just putting the plus there to emphasize that it's positive. It's not necessarily needed. So we've got that number plus this number. Okay, so that's just 559 minus 488. $71. So delta E is 71, and that's a positive 71 joules. Overall, the system gained 71 joules of energy. Any questions? Yes?
And it always going to be positive? Or
No, the delta E could be positive or negative.
and that depends on the number?
It depends on the sign of these and their relative size. So if it had done more work, maybe if it did minus 688 joules of work, then overall the energy change would be negative. So it can be either.